So this video is going to be a quick reminder of how we factor, why we factor, and some of the patterns that we're looking for when we're encountering a factoring problem. Okay, so first sort of big picture questions is why are we factoring anyway? What's the purpose behind factoring? And so some of you might recall that we sometimes have these lovely problems, right? Like where we've got x squared, maybe plus 5x plus 4, and that problem might be set equal to 0, right? And because we don't have a really good method for dealing with having an x squared, particularly when there's also a linear term, right? So we have a quadratic term here and a linear term. Um, and if we start moving things around, it's like we can get the linear term on one side, but we'll still have the quadratic term maybe on the other side. So it's harder to isolate that x. So we need a different method other than just isolating the x, to solve and find out what value that x might hold. And so one of the most efficient methods to use is to see if we can figure out, hey, what did we multiply together originally in order to get this quadratic trinomial? What were the two linear factors, right? So I'm trying to reduce the order of this problem from a quadratic problem down to a linear problem. If I can figure out what are the two linear binomials that multiplied together to give me the quadratic trinomial, then I can use this little trick with the zero product property and find a method to solve it. So here I'm trying to take this x squared and I'm going to say, well, what was it if x times x gave me x squared? What gives me the rest of this polynomial? And so remember, I'm finding the two things that multiplied together, right? The product is 4x squared, and they add up to the 5x in the middle. So here I've got the x squared part already, so I need it to be 4x squared when I multiply together, and they need to add up to 5. So two terms that would multiply to 4 and add to 5 would be positive 4 and positive 1. So my two factors for this trinomial are x plus 4 and x plus 1. And you might remember that the zero product property tells us that if two things are multiplied together and they result in 0, either of those two things could have been 0, right? If the first term was 0, if x plus 4 was equal to 0, then 0 times anything equals 0. And vice versa, if the second term was 0, then 0 times whatever the first factor was would give me 0 as well. So I could say that x plus 4, that first factor, if that's equal to 0, that's a possible solution for this equation. And also if x plus 1 is equal to 0, that's another, oh, my bread's done. That's another possible solution for this problem. So then I can solve both of these linear equations and I can get x is equal to negative 4 and x is equal to negative 1. So again, the goal of factoring is to take something that's a higher order, a quadratic here, and try to get them down to linear factors, ideally that are set equal to 0, so we can use this zero product property trick to solve. Much further down the road, you will even see things that are higher orders than quadratics, and often it is possible to factor those as well. But the goal always is to try to reduce the highest term, reduce the power of the highest term, ideally to get it down to a linear, sometimes a quadratic, but ideally to get it down to a linear factor so that you can solve effectively. So I'm going to talk for a minute here about this lovely flow chart that I made. And basically this is just sort of a reminder, a refresher of a lot of different methods that we know, but also sort of to try to help give you a hierarchy of what to do first. So the first thing you always want to do is check if there's a GCF. There's a lot of reasons for this, but you might be able to factor out a GCF that is a variable. So you might be able to get the polynomial to be linear without having to resort to more difficult factoring terms. And also, you might be able to just to reduce the size of the numbers, right? By finding a greatest common factor that you can factor out of all of the terms, you can make a much more efficient problem. Once you've factored out the GCF, then your next goal is going to be to count the terms, okay? Because that's going to give you a good sort of trick about what's coming next. If you have two terms, chances are likely, or you're at least going to want to check for whether you have a difference of two squares. And we'll look at what that is in just a moment. If you count the terms and you've got three terms, then you might have something called a perfect square trinomial, which would be a nice pattern, and you could probably do that then mentally. Or you might have one of the ones where you've got to figure out what are the two things that multiply together to give you A times C, and what are the two things that, those two factors of that would add up to your B, so you can split it into four terms, right? If you have four terms to start off with, then you can go straight into factoring by grouping. Again, if you don't have three terms, and it's not this perfect square trinomial, you're going to use the product and sum to make it four terms, and then you can come down to the factoring by grouping. So let's take a look at these two ones that I mentioned here. This either difference of two squares pattern or this perfect square trinomial pattern. Because these are ones that if you can recognize them and identify them, you can sort of do them more in your head, right? It can become sort of more of a mental math puzzle. And so I want to talk those through those real quick. Difference of two squares is exactly what it sounds like. So the first term that you have in the in your polynomial, this is a perfect square, right? So 9x squared would be 3x times 3x would give me 9x squared. And this second term is also a perfect square, right? Because 4 times 4 would give me 16. And you'll notice, if you're, really careful and sort of look in the middle there, it's a difference. It's a subtraction problem. So in order for it to be a difference of two squares, it has to, one, be a subtraction problem. And it has to have two terms that are both perfect squares, okay? If that's the case, then it has this really neat pattern to it because something had to happen with your factors to make the middle terms cancel out. So if I take this first term, I know that this first 3x has to be multiplied by 3x to give me the 9x squared. And I know that whatever the second term was had to cancel out with the first term. So if the only way that could happen is if one was a positive and the other was a negative. So for example, I'm just going to check that I did that correctly, right? 3x times 3x to multiply it out would be 9x squared. And 3x times negative 4 is negative 12x. And 4 times positive 3x is positive 12x, and 4 times negative 4 is negative 16. So these middle two terms cancel out, and lo and behold, that was my original problem. Again, if you can identify this pattern, if you can say, hey, look, that's a square, and that's a square, and that's a difference, then you know that you've got to have two factors, one of which is an addition, and one of which is a subtraction, so they can cancel out. And you know that the first term has to be the square root of the first term in the binomial, and the second term has to be the square root of the second term. So you can do them pretty mentally. Now, don't forget that you always have to check for a GCF first, because a GCF could be hiding something. For example, 20 is not a perfect square, but what if I factored a 5 out of this binomial first? So now I've got 4x squared minus 9. And so now look, I've got a perfect square and a perfect square. So my final factors are 2x plus 3 and 2x minus 3. Okay? So difference of two squares is definitely worth looking out for. Some things to note is that it's got to be a subtraction problem, right? And they've got to both be squares. Otherwise, you might just have a prime binomial. One other pattern that is a great mental math trick or gives you sort of a great mental opportunity is if you have a perfect square trinomial. And a perfect square trinomial is ones where when you factored it, which you could do using the grouping, the splitting into 4 and doing the grouping, but when you factor it, you're going to notice that the middle two terms are identical. So for example, if I were going to do this the sort of old-fashioned way and do a times c, I would see that that would be 16x squared, and then I want the two terms that added together give me negative 8x. So notice that whatever the two terms are, they've got to be add to negative 8, and so it's going to be negative 4x and negative 4x that would add to negative 8. So these are the same, okay? Another way to look at it is if I were to take the square root of this a times c, right? The square root of 16x squared is 4x. And double that, right? So 4x doubled gives me this central term, right? So this is the double of the squares of a times c. Okay. And now you do need to be a little bit careful with the signs, right? Because the square will always be positive, but the central term could be negative like it is here, which means that you're going to deal with a negative 4x and a negative 4x. Now, the reason that this is nice if we can identify it is because I can go right ahead and I can say, hey, it's got to be x times x that gives me x squared, and it's got to be 4 and 4 that give me 16. And since it's just doubled, it's just the same factor squared, right? The same factor twice. So again, x squared and 25, that's 25x squared. The square root of that is 5x. Double it, it's 10x. So this is a perfect square trinomial, and the factors are x plus 5. Take a look here. So here, this one's a little bit different because I've got a 4 in the front, but still I'm going to multiply my a times my c, and I'm going to get 4r squared. And 4r squared is a perfect square. The square root of 4r squared would be, that's right, 2r. Doubling 2r gives me 4r, so that means that my factors squared are 2r plus 1, because the square root of the last term is 1. Cool, right? Take a look here. There might be something that goes into these, right? There might be some sort of common factor here. So I'm thinking maybe 5 goes into everything. So 5 goes into 80. There might be a bigger one. Ooh. Well, let's start with that. So if 5 goes into, excuse me, 80, that's 130, 16k squared minus 40k plus 25. Okay, so now is that a perfect square trinomial? Well, if 16k squared is a perfect square and 25 is a perfect square, and so if I multiply those together, 25 times 16, that's 30, that's 15, that's 5, and that's 2, and so that's 3, nope, I was rushing. That's 400. And so 400 is in fact a perfect square. It would be 20 times 20. So if I took the square root of 400, I'll do that down here, I would get 20. And if I were to double 20, I would get 40. Wow, that's pretty cool. So I've got 5, and then the factor that's squared is the square root of the first term, 4k, the square root of the second term, 5, and it's got to be a subtraction problem because I had to get a negative 40k in the middle there. Cool, right? So you're going to need a little bit of practice with these. I've been doing these for about 25 years or so, so you won't be quite as fast as me at the beginning. But first we're going to sort of make sure that we can identify them, and then we'll work on some strategies to start factoring them. Okay, great. I hope this helped. Thanks.